So today's lesson is going to be over something called a Lewis diagram. And a Lewis diagram or an electron dot diagram is where we show the number of valence electrons around elements. And then the Lewis diagram specifically is when we show the compound. How did the electrons get shared between the elements that are involved? And so we're going to start out with a review of what an electron dot diagram is, or a Lewis dot structure, whatever you guys wanted to call it. It's just how we represent a visual representation of what's happening to those valence electrons around the element symbol. And with that, you're looking for just a representation, a model to show that those outermost electrons that are involved in chemical bonding. So you're going to treat the element symbol like it has four distinct sides. And you're going to draw dots to represent the valence electrons. And I always start on the north side and go around clockwise, but there's not a rule that says to do that. That's just my consistent way that I do the problems. So first of all, you have to know how many valence electrons are in each group. So hydrogen is in group 1. Everything in group 1 has one valence electron. So to do the dot diagram, I'm going to draw the element symbol, and then I'm going to start the north side. I'm going to put one single dot because it only has one valence electron. Beryllium is in group 2. Everything in group 2 has two valence electrons. So I'm going to start on the top, one dot, go to the right, two dots. Boron is in group 13. Everything in group 13 has three valence electrons. So I'm going to start up here, 1, 2, 3. Carbon is in group 14. Everything in group 14 has four valence for the ones that are going to chemically bond in a covalent manner. So I'm going to start 1, 2, 3, 4. Nitrogen is in group 15. It has five valence electrons. So I'm going to go 1, 2, 3, 4, 5. And then oxygen is in group 16. It has six valence electrons. 1, 2, 3, 4, 5, 6. Fluorine is in group 17. It has seven valence electrons. 1, 2, 3, 4, 5, 6, 7. And then neon is, I'm going to put it up here, in group 18. It has eight valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Now the deal is that anywhere that we see these single dots, that's where it can chemically bond. So hydrogen can bond once, beryllium twice, boron 3 times, carbon 4, nitrogen only 3, oxygen only 2, fluorine only 1, and neon none. Anywhere it's paired up, that means that it's already stable in that location. Most elements want to have 8 valence electrons for stability so they can be like the noble gases. Now our exception is helium. So helium has 2 total electrons, so it has 2 valence electrons, but we do not draw it the same way as beryllium because beryllium is very chemically active, but helium is not. So we actually draw both of our dots on one side for helium. Doesn't matter which side, just one side. So a Lewis diagram is how we show that the elements form the compound. Again, most of the elements want to have that octet of electrons, the 8 valence electrons, but there are some exceptions, and you need to be familiar with these. One of them is hydrogen. So hydrogen is always stable with only 2 valence electrons. That is all it can hold. It can only fill up that first energy level. If you want to think about Bohr's model, in Bohr's model, remember you have your nucleus in the middle, and then you have your energy levels outside of your nucleus. So this would be my nucleus. So let's say that I was talking about hydrogen. Well, hydrogen has 1 proton, so it has 1 electron. It only needs 1 more to fill up this first ring. The other elements have to fill up the second ring in Bohr's model. That's the reason almost all the elements have to get to that 8 valence electrons. Even like the 3rd, 4th, 5th energy level, most of them still want to get to that 8 valence electrons. And so hydrogen is always stable with just 2 valence electrons. Beryllium, even though it's a metal, its electronegativity makes it sometimes bond covalently. It doesn't always bond ionically. And so because of that, it can actually share electrons even though it is a metal. Usually a covalent bond is between nonmetals or nonmetals and metalloids, but this is an exception. And it's okay with only 4 valence electrons. Remember on the last page, I showed beryllium like this, so it can bond 1, 2 times. And it's okay with that. And it's okay with only having those 4 valence electrons whenever it goes to share. Boron is able to be stable with only 6 valence electrons. So here, if we look at this, boron normally has 1, 2, 3. It can bond in any of those locations. When a bond forms, it is now sharing 2 electrons. So if it has 1, 2, 3, then it can actually share 2, 4, 6 electrons around it, and it's okay with that. Again, it's not going to reach its octet. These are what we call incomplete octets. It means that they are okay with having less than 8. They are incomplete. Covalent compounds share electron pairs. We're going to start out with only single bonding. So we show the shared pair between 2 elements. Instead of writing dots for the electrons, we show it as a dash or a hyphen. And so let's do several examples, and let me walk you through how you need to do these Lewis diagrams because they're like a little puzzle. So when you're doing these problems, you want to figure out the total number of valence electrons that are available. That way you don't add in any dots or take away any dots. So nitrogen is in group 15. It has 5 valence electrons. Hydrogen is in group 1. It has 1 valence electron, but there are 3 of them. So 5 plus 1 plus 1 plus 1 gives me 8 total electrons. So I got to have total of 8 electrons here. You're going to always want to start out with figuring out a skeleton structure, and this is going to get easier the more you do these, but you're always going to put the element that can make the most bonds in the middle. So nitrogen can make 3 bonds, hydrogen can only make 1. So nitrogen is going to be my central atom. So I'm going to put nitrogen in the middle, and I'm going to draw nitrogen's normal structure. Then I have 3 hydrogens. I also have 3 lonely dots. So each hydrogen is going to come in and bring its 1 lonely dot with it. Once it is sharing those electrons, we change those pairs of dots to a hyphen or a line. So you will just change it out. And once you get good at this, you can skip this step and just go straight to drawing the line. So then we want to make sure that we have everything is stable, and we've only used 8 electrons. So have 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8 around it. It has to have an octet. Hydrogen only has 2, and that is correct because it always has that incomplete octet. Next one is HCl. Hydrogen's in group 1, so it has 1 valence. Chlorine is in group 17, so it has 7. So it has a total of 8 valence electrons also. Now this one doesn't have a central atom for my skeleton structure because there's only 2 elements. So if there's only 2 elements, all they can do is bond together. So I'm going to have hydrogen come in with its 1 electron. Chlorine's going to come in with its 7. And again, I'm going to make a line to show the electrons that are being shared between those elements. This is a model representing what's happening in true chemical bonding. So I have 2, 4, 6, 8. That's how many I need. 8 around chlorine. It has to have 8. 2 around hydrogen. That's all it needs. I'm going to clear these out so I can have room to do my next ones. So SiCl4. So Si is in group 14, so it has 4 valence electrons. Chlorine is in group 17, so it has 7, but there are 4 total chlorines, so that's going to be a total of 28 plus 4. So I have a total of 32 electrons I got to do something with. Silicone can bond 4 times. Chlorine can only bond 1. And so I'm going to put silicone as my central atom. It has 4 lonely dots. I have 4 chlorines. Each chlorine is going to come in and bring their electrons. It has 7. It only needs 1 more. And these actually become chemical bonds. Again, as you become more comfortable with this, you will not need to draw the dots. You can just draw straight to the bonds once you get comfy with that skeleton structure. Now let's check and make sure that we have 32 total electrons. So I have 2, 4, 6, 8 around silicone, which is right. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And each chlorine has 7 valence electrons, so everything has a complete octet. BF3. Boron has 3 valence electrons because it's in group 13. Each fluorine has 7, but there are 3, so that's a total of 21. So I have a total of 24 electrons I have to do something with. Boron can bond 3 times. Fluorine can only bond once, so boron is going to be my central atom. These 3 lonely electrons are where my fluorines are going to come in and bring their electrons. Again, these pairs are going to become lines. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So everything has been used, but boron only has 2, 4, 6 electrons. That is okay because boron is one of our things that is an incomplete octet, and so it is absolutely okay with only 6. Fluorine must have 8, but boron does not have to have 8. So then I have BeH2. Beryllium is in group 2, and hydrogen is in group 1. Beryllium has 2 valence. Each hydrogen has 1 valence, so that's 2 plus 1 plus 1 gives me 4 electrons. Beryllium can bond twice. Hydrogen can only bond once, so beryllium is going to become my central atom. Beryllium only has 2 valence electrons. It really doesn't matter which sides you put these dots on. I usually spread it out and try to make it be symmetrical around the central atom as much as I can. And that'll make more sense when we get to talking about 3-dimensional shapes. Right now we're doing 2-dimensional shapes. And so I have 2 lonely electrons and I have 2 hydrogens. Each hydrogen is going to come in and bring its electron. Those are going to become a bond. So around the beryllium has only 2, 4, and hydrogen only has 2, but that's okay because hydrogen is always going to only have 2, and beryllium is our exception. It is a metal, but because of its electronegativity is very close to the electronegativities of other nonmetals, it ends up bonding covalently. And so it is okay having that incomplete octet of only 4 electrons. H2O, so hydrogen has 1 electron each, that's 2 total. Oxygen's in group 16, so it has 6 valence electrons, so 6, 7, 8. So I got a total of 8 electrons I got to do something with. I'm going to put oxygen in the middle. I'm going to distribute my hydrogens on either side. They would have brought in their 1 electron, but we just know that they're going to bond. This is the step that you can start skipping once you get comfy with it. Oxygen has a total of 6 electrons, so it has 2, 4, and then I had my 5 and my 6. And so with that, we have 2, 4, 6, 8 we've used. Around oxygen is 2, 4, 6, 8, and hydrogen is only 1. Hydrogen can only make a 1 and done. It makes 1 single bond and it is done. It can never do anything more than that. And so that is the structure for water. Again, you could have put the hydrogens on top and bottom or on the top and the right. It doesn't really matter. I just spread them out evenly because it's going to make a bigger difference on a later lesson. So then this last one is C3H8. So this is called an organic compound. Anything that has carbons is organic. And we've seen these. These are hydrocarbons. We saw them when we talked about the combustion and empirical formula of an organic compound. So what they do is in organic compounds, they often link all of the carbons together and then everything else comes off of those carbons. So I have 3 carbons and 8 hydrogens. Each carbon has 4 valence electrons, so that's going to be a total of 12 electrons, plus my 8 electrons, so I have a total of 20 electrons I've got to do something with. What happens is the carbons link together. They're going to make a chain. That's the reason carbon is so common in so many different things, is because it can bond in a variety of ways and it can link together. So I have my 3 carbons, they've bonded, and I have 1, 2, 3, 4, 5, 6, 7, 8 lonely dots, and I happen to have 8 hydrogens. So each hydrogen's going to come in and share its lonely electron with carbon. And it's going to fill in all those lonely electrons all the way around the C3. So now I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, which is how many I had. I have 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around carbon, and each hydrogen only has that 1 because they're 1 and done. So it's a puzzle on these. You start somewhere, and you don't have to make these lines. You can always do those dots until you're ready to make the lines after. So if you don't feel comfortable immediately starting with that skeleton structure with the lines, then whenever you're doing these problems, you can just do it like I showed you before, where hydrogen brings its electron. So then I have 2, 3, 4, 5, 6 around my oxygen, 1 around each hydrogen, and then they go ahead and bond. So you can do that after if you need to. Sometimes There are some exceptions that we have that are what we call expanded octets. Sulfur and phosphorus are the most common. You're going to run into these. There are some other nonmetals, but these are the two that AP is going to expect you to know. Sulfur can do what's called an expanded octet, and it can hold up to 12 valence electrons. Phosphorus can expand and hold up to 10. And then krypton and xenon, and both can do expanded octets where they end up with